Yes, okay. So let me begin. Hi, I'm Ayer Balasubramanian, and I'm a PhD student at the Technical University of Munich. And today I'll be talking about complexity of coverability in bounded path broadcast networks. So let me begin by first telling you what broadcast networks are by means of an example. So broadcast networks are a model of distributed computation in which we have some collection of agents. And all these agents execute the same underlying finite state protocol, and they communicate to each other by means of sending and receiving messages. So for instance, in our example, we have a protocol with 4 states: the red bird state, the blue bird state, the green bird state, and the cool state. Okay. And we assume that initially all the agents begin at the red bird state, which is the initial state. And then the transitions allow agents to send and receive messages. So for instance, the self loop on top of the red bird state allows an agent to send the message blue and remain at the same state. While this transition, moving from the red bird state to the blue bird state, allows an agent to receive a message blue from some other agent and move from the red bird state to the blue bird state. For the sake of brevity, we assume that if I don't mention what happens to a state upon receiving a message, there is simply a self loop there with that reception. For instance, I have not mentioned what happens at the cool bird state upon receiving the message blue. So I assume that if an agent is at the cool bird state and receives the message blue, then it simply discards the message and simply stays at the same state. Similarly, we have transitions for other messages. For instance, we have a transition for sending and receiving messages sending and receiving corresponding to the message green, and then also corresponding to the message cool. Okay, so this is what constitutes a protocol. So in a broadcast network, we are given a protocol, and we are also given some graph, any graph on any number of nodes. Okay, such that each node is labeled by some state of the protocol. So the intuition here is that you can think of each node having an agent. Okay, and then these nodes send and receive messages to its neighbors according to the transitions of the given protocol. So in our example here, initially we take the path graph on 4 nodes, and all of these nodes are labeled with the red bird state, just the initial state. So we should think of this as having 4 agents, each of which start at the initial red bird state. And then at each point in time, an agent can send a message according to the transitions of the protocol, which is then immediately received by all of its neighbors. So in this sense, the agent is broadcasting a message to all of its neighbors. For instance, let's say that the leftmost agent broadcasts a message blue. This is then received by its only neighbor, which is the second agent. And this agent, upon receiving the message blue, moves to the blue state, as is indicated by the transitions of the protocol. Now, let's say the blue agent, the one in the middle, broadcasts the message green. This is then received by both of its neighbors on both ends. Okay, and both of these neighbors, upon receiving the message green, now move to the green state. Okay, and then finally, let's say the green state, the third agent, which is in the green state, broadcasts a message cool. This is once again received by both of its neighbors, and by our convention, the blue bird just forgets this message, just simply stays at the blue state, whereas the red bird receives this message cool and then moves to the cool bird state. So what we have given here is we started with an initial graph, that is a graph in which all agents started at the initial state, and we have given an execution in which some agent has reached the cool bird state. So we call this an execution covering this state, covering the cool bird state. Okay. So with this notion of coverability being introduced, we can then ask the following question. We are given a protocol P and a state, some state F of the protocol. And we are asked to decide if the state F can be covered from some initial graph. I mean, we are allowed to take a graph of any size. The only constraint is that initially we have to label all the nodes with the initial side of the protocol. But from any such graph, can we reach a point where some agent is in the state F? Okay. This problem was proven to be undecidable by Delzano et al. And in the same paper, they consider a restricted version of the problem, which they call bounded path coverability. So here, in addition to a protocol and a state F, we are also given a fixed number. We are also given as input a number K. And we are asked to decide if the state f can be covered from some initial graph whose longest path is bounded by k. Okay, so once again, we have to take any initial graph, but with the exception that the longest path in that graph should be bounded by k. Now, since the underlying graph does not change along an execution, if the initial graph has this property, then this stays invariant along any execution from that initial graph. So in any execution, the longest path will still be bounded by k. And the authors prove that this problem is decidable. Our main result is that we give a complexity theoretic result for this problem. That is, we show that this problem, bounded path coverability, is complete for a class called f epsilon naught. Now, this class is not, it's not very popular. So this is a class which is, this is a complexity class in the so-called fast-growing hierarchy of complexity classes. And to define this formally will take a lot of time. So what I will do is instead is I'll present some well-known milestones of this hierarchy and then relate this f epsilon naught class to the milestones of this to give you a sense of how big this complexity class is and how hard bounded path coverability actually is. So one of the milestones in this fast-growing hierarchy is the so-called F3, the tower complexity class, which is already so huge that it contains non-elementary problems. That is, problems which cannot be solved in time to the fixed exponent with running time to the fixed exponential tower of a fixed exponential height of in the input size. Okay, so this is already so huge. And then we have an even bigger class beyond this, which is the so-called Ackermann class, which contains non-primitive recursive problems. And then we have another class even bigger than this Ackermann class, which is in some sense even harder than this. It's called the hyper-Ackermann class. And epsilon naught should be thought of as the limit of the ordinals taken by starting from omega and then going to omega to the omega, omega to the omega to the omega, and so on. So epsilon naught is like really huge, and f epsilon naught is its corresponding class. So this, I hope this gives you an indication of how big this class really is and how hard bounded path coverability as a problem actually is. So with this, that's all for this presentation. Thank you for listening, and I'll be happy to take any questions.
Thanks, Balasubramaniam, for the talk. We have time for questions. Maybe I will ask one question. So is there a way to formulate some kind of a reachability problem here? Like coverability is just asking whether any one state can be reached by any reachable configuration. Is there a way to formulate or have people studied formulations of the question where you ask more precise questions like
maybe so all agents reach the same state, for instance? That might be one question.
Yeah, that might be one. Or maybe just two states, for example. Is there a configuration where one state reaches the blue bird and another reaches the green bird?
Yes. So this two states, I think. So because this is a very structured transition system, or so in some sense, if you can check whether an agent reaches a blue bird and an agent reaches a green bird, then it's possible to sort of execute these two things in a disjoint way and then have an execution in which both are covered. You have to take you have to take two copies of this execution, like one copy of the execution executing the blue bird, one copy of the execution covering the green bird, and then sort of put these two together. That's the.
Okay, but then you will have to start with disconnected graph.
Yes. No, you can make it connected even without this, but okay. So okay, but I don't know if that will immediately preserve the bounded path property. this works for like any graph. I mean, you can do this with, but even so, I don't know if it preserve the bounded problem.
Okay.
I mean, of course, you can make it disjoint, and you can cheat in that sense, make it disjoint and still
Yeah.
have it.
Okay.
But I don't know if you can keep it correct. But that's a good question. Yes. But essentially, anything stronger than this, it becomes undecidable. Even asking all agents reach the same state, it becomes undecidable.
Yeah, understandable. So this is one more question from Narayan Kumar. It says,
Okay.
are there any other natural problems complete for this complexity class f epsilon naught?
Yes. So in fact, the result that I prove in this paper is proved by giving a lower bound. Is proved by giving a reduction from some other problem, which is not just the Turing machine acceptance problem. So it's the coverability problem for nested counter systems. So it works with trees. So you have counters upon counters which can have counters themselves, which can have counters themselves, and so on, and then addition and subtraction with these.
Okay.
And for that, and for that model, the coverability problem is f epsilon not complete.
Okay. Any other questions?
Hi, this is Akshay. I had a quick question, if there is time.
Yeah, we have 1.5 minutes. Yes, go ahead.
Oh, excellent. Great. Hi, Balasubramanian. Thanks for the talk. Maybe possibly a naive question. So what is the dependence on K? Is that, I mean, can we say a little bit more about the parameterized complexity?
Yeah, no, I mean, that's actually a very nice question. So in the paper, I didn't concentrate on this much. I just wanted to prove this f epsilon not hard problem. But as I said, so since I give this lower bound by giving a reduction from this coverability for nested counter systems, there is a parameterized result for this coverability for nested counter systems. So depending on how many nested counters you can have, the hardness roughly goes from omega to omega to the omega to omega to the omega to the omega and so on. I mean, I'm not fully sure of this, but this is, I think, roughly as it goes. And I think I give a reduction from K nested counter systems to 2K bounded path coverability. So then we should also get
nice
omega to or like omega and then omega and so on and so on. Yeah, but that and for nested counter systems, even though the low, I mean, it's not, we don't know of tight. I don't think we know of tight parameterized upper bound. So we know a lower bound, but we have an upper bound which does not match the lower bound with respect to the parameterized part. So the same is also, I think, true for this. But thanks for the question. It's a very nice question.
Yeah, thanks for the answer. That clarifies. Thanks.
Okay, so that's actually just matching the time bound. So let's thank Balasubramaniam.
Thank you.
And we will move on to the second talk by Monish Bhattacharya. We'll be talking about Parikh images of register automata. Yes, Monish, over to you. Manish, we can't hear you. You're on mute or something?
Okay, sorry. Okay. So I hope you can hear me and you can see the slides, right?
Yes.
Okay, thanks. So my name is Monish, and I will talk about Parikh images of register automata. It's a joint work with Slovak Lasota, and we are from University of Warsaw. Okay. So for some reason, the slides are not moving. Okay, so can you please?
Yeah.
Okay, so I have a backup slide, so I will use that. Okay, so. Can you see the slides now?
Yeah.
Okay.
Yes.
Okay, so our motive was to look for Parikh's theorem for infinite alphabets. Okay, I'm still facing some technical issues
So
here.
maybe you can just zoom out and use the normal view. Yeah, now
Oh,
we can see. Yeah.
okay.
Now it's better.
So infinite alphabet. So the basic one we are the one which we are considering is a countably infinite set with only equality relation. So, and the automaton, we call them as atoms or data or letters. And the automaton model we are using is the classical non-deterministic register automata. So it is a finite automata with some finite registers, and it can store these data values and compare with input and change accordingly, according to the transition rules. So, okay. So the previous results which we have shown is, so it is well known that for finite automata, the Parikh images are semilinear sets. And so one of the results which shown previously shown is the natural extension of semilinear sets, which is basically replacing all finite by orbit finite union, and the indexing set as orbit finite set is not sufficient. So in fact, there is what is shown is there is an one non-deterministic register automata language for which the language doesn't have this semilinear set property. Okay, and another one was, so in fact, indeed, for one non-deterministic register automata, we showed this Parikh images are rational, which is an extension of semilinear sets. Now we can concatenate semilinear sets and compose semilinear sets in the place of periods and so on. So we also showed that for for a context-free language with one register, the Parikh images are still rational. So this gives like a Parikh kind of theorem for at least one register automata. So far I have shown the existing results. What in this work we introduce a new a strict syntactic subclass of register automata. We call it as hierarchical register automata. So the main idea is the registers are ordered. So now we can talk about lower registers and higher registers. So the main idea is, so if I want to change a lower registers, let's say K, and all the registers which are lower than that are preserved, and the registers which are higher than K are not preserved. So it may not be preserved. So for example, if I want to change A2 in the second register, so I change it to some A2 prime. And what this transition might also do is it can change the third register or fourth register. So we don't have any control over the registers which are higher. Okay, and another way to think about this register, this automaton model is, so let's say the registers are arranged in a stack in an ordered fashion. And if I were to change the register 2, I am popping all these 3 guys and pushing 3 new guys. Okay. So what we the main result of this paper is rational languages, which has like this rational data vectors as Parikh images are Parikh equivalent. So they have, so the hierarchical register automata collides with the rational set of Parikh vectors. So there are, so in what we show is that every rational language is recognized by HRA, and HRA have rational Parikh image. So this comes from the fact we can easily see that because one register automata is contained in this hierarchical automata, and there are there are languages which are not semilinear in that sense. Okay, so as a corollary, what we get is register automata. So if there is some register automata has a rational Parikh image, it has to be Parikh equivalent to some hierarchical register automata. And so indeed, it's like it's a strict subclass. So, and so there are plenty of open questions here. So the first one is, can we whether we generalize this Parikh's theorem to K registers? And another one is we can look at for another orbit finite alphabets, which are like pairs, tuples, etc. And so in case of finite finite automaton, we know that the Parikh images collides to star height 1. So it is not known that this rational images of register automata, Parikh images of register automata is like converging in that sense. And we also don't know anything about given to rational data vector, we can decide equality, intersection, and etc. So that's all I have to say. And sorry for the technical issues in the beginning. So,
thank you for the talk, and we have time for questions. So one question I have is, so given a language or an infinite alphabet,
yes.
Let's say in some other representation, is it decidable to check whether it can be accepted by a hierarchical register automaton?
So basically we have to construct so if it is given as a rational expression, we can do it. So this is there is a the proof goes like this. It goes on the induction on the rational expression.
Okay.
But in
general, suppose you are just given a arbitrary register automaton. The question is there an equivalent hierarchical automaton?
But that is the open question, right? So it means that you mean like Parikh equivalent or equal? So there are two equivalents.
Here I'm talking about language equivalents. Just to understand this class of languages that you're defining. Yeah.
So we don't know this.
Can I ask a quick question?
Yeah.
Yeah. Yes, please.
So yeah, you are generalizing to KNRA as an open question. What happens if you've got one alternating register automaton? One. Sometimes that is a little better behaved.
So we didn't investigate one alternating register automata. So it's a good question, and so I don't have an answer. Sorry.
Well, your co-author is an expert in all this. Yeah. Okay. Thanks.
Yeah, thanks.
Any other questions? Okay, if not, then let's thank the speaker. Thanks, Monish. And we'll move on to the third talk, which will be given by Sparsa Roy Chaudhary on time systems. Over to you, Sparsa.
Just sharing my screen. Yeah, is it visible?
Yes.
Yeah, thank you. So I'm going to talk about resilience of time systems. So this is a joint work with Professor Akshay, Professor Blaise Genest, Professor Loic, and Professor S. Krishna. So the basic motivation of this work is, suppose you are going on a train from location A to location V, and the train gets delayed in some location between, possibly in C. Now it's immediate question that comes into our mind that what happens, can we reach our destination on time? So to cope around with, the railway transition system can add some extra operation that can actually gain the delay so that it comes back to time. Some mechanism it can add. Now the immediate question that comes to our mind is the mechanism sufficient to allow for all possible delays or some possible delays to make sure that the run goes back into normal behavior, the train comes back to normal behavior. So as a timing are associated with it, because a train always should go by a timetable, and time automata is used to model this kind of situations. The time automata is a finite state machine coupled with a finite number of real valued variables called clocks. And the transitions the clocks are used to measure the time difference between two corresponding events. For example, the normal behavior of this train is like it starts from a station represented by the state L1, and it can choose to stay on a station within 1 or 2 time units, which is modeled using the clock Y, and then it departs from the station, and the L2 represents the state of running, or the running state of the train. Now, after leaving a station, it is required that it should reach the destination station within 4 units of time. To uniformly distribute the complexity of the train transit system, we are assumed that the train stays on a station within from 1 time unit to 2 time units, and it takes at most 4 time units to reach from one station to another. So the green is the good behavior of the system. That means when no delay has occurred. Now this train transition system has another mechanism. Suppose a delay occurred during the arrival from one station to another station, then it can choose to skip a station when the next station is not a destination 1. So by skipping this station, it gains some time, and then by gaining, it can actually recover some amount of time that is lost because of the delay. Now the immediate question is this mechanism sufficient, right? So to cope around this problem, we propose the 2 main things that we have to understand. The first is that time automata doesn't allow us to this kind of behavior, like it expects the system to behave as modeled properly. But in real world, it is not the case. The fault is pretty common, and we need to model the fault as a part of our system. So to add this extra fault, we propose a new fault model which maps every action to a corresponding rational number, which represents the possible delay of the action. For example, in the previous example, we have a fault model that maps a 2 amount of possible delay to the arrival action. Now, how we encode this, add this extra fault model into the model of the time automata. So for example, suppose this is the basic definition of a guard, or rather constraints of a time automata, where from location 2 to location 1, it is expected that the arrival should happen when the clock value is less than or equal to 4. Now, if the delay happened, then that means, because it can happen like at most 2 time units, so then the arrival can happen, the clock value during the arrival can be much bigger than like 4 to 6. It can, the upper bound of the constraint will be increased by the fault model. Now, in this model, in this transition, there are 2 parts. One, which is good behavior. That means in this model, it can still happen that when the arrival happens, the clock value of x is less than or equal to 4. But the faulty part will only happen when the arrival happens at the clock value x within 4 to 6. Now we call this kind of transitions faulty transition. Now let us go back to our previous model where we encode this faulty transitions, and then we can take, or the driver can choose to take the recovery mechanism. Now for example, when the delay happened, so for example, this is normal behavior from L1 to L2. Now when the delay happened, then this transition will be taken, and then it can choose to take the recovery mechanism so that it can recover the delay time. Now, given this definition, we first define 2 important definitions for our word. One is the faulty word. The faulty word is a word where it has at least one event which is fault. And just faulty word, we say, is a subset, is a prefix of a faulty word which ends with the first fault of the behavior. Now we call a run is faulty if it reads a faulty word, and a just faulty if it reads a just faulty word. Now we give definition of fault back to normal with the current definition of a faulty word. So we say the faulty word of length n comes back to normal within k steps if there is a suffix after k steps of the fault that matches with a suffix of a good word that is accepted by the original automaton. Now we also consider this back to normal definition for untimed words. Then we will call it an untimed back to normal behavior. Now let's define this back to normal behavior with the same example that we had previously. Suppose this is a 2 word we have taken. The first word is faulty word, where it has a delayed by 6. The arrival happened at 6 time units. When the value of 6, that means this transition is taken. Then the driver chose to cover up the delay using the mechanism. So this is a 4 steps it requires to come back to the normal behavior. Why it is back to normal? Because there exists a good word accepted by the original automaton, which is something like this. And look at this green part is a suffix which matches exactly the same with the faulty parts, faulty suffix. Now, given this back to normal definition, we propose two resilience problems. We say a system with a recovery mechanism is a for all resilience when every faulty word can back to normal with k steps. That is why the k is a parameter. That is why it's called k for all resilience. And if for every just faulty word, we can find an extension of the faulty word, and for that extension, along with the, like, for example, W1F is the just faulty word which ends with a fault. Now we can find an extension W prime such that the run or faulty run W1F followed by W prime is back to normal. Then we will call the system is K for K exists resilience. Now, these are the following results that we have. Time for all resilience we have shown for normal time automata is a very hard problem. In fact, it is undecidable. And we have shown this result by reducing the problem to language inclusion problem of time automata, which is known to be undecidable. But when we consider a subclass of time automata, which is integer reset automata, where the clocks can be only reset during the integral value of the real timestamp, then this problem is X-space complete. Now we have studied the problem for untimed cases also. So universal resilience for untimed automata we have shown that is X-space complete. But when we go to existential resilience, we have shown that for time automata, existential resilience is X-space. To show this X-space, like that this problem belongs to X-space, we have used a special technique, a refinement of region automata, which we call a strong region construction, which also encodes the global time regions into the regions, so that it helps us to solve the problem of existential resilience. But the hardness we are able to show that it's p-space hard, so we are not able to close the gap of the complexity, so it belongs to the future work. For untimed existential resilience, we are able to show that this problem is p-space complete. And for future work, so the immediate future work that comes to our mind is, instead of the case steps, to consider that after the fault, can we spend some amount of time, suppose for a given time t, can we come back to normal behavior within t units of time? And the resilience, we can also think of, we are already studying resilience on integer reset automata as a subclass of time automata, but there are other subclasses of time automata such as event recording automata, etc., on which it will be interesting to see how resilience is performing, or how difficult the resilience problem on those subclasses. The next is that on more complicated system, for example, with recursion, with randomness, etc. So thank you, and I'm ready to take questions.
Thank you, Sparsha. We have time for questions. So one question I have is, in your exponential space upper bound, so what goes to the exponent, which is the parameter of the input instance that is really causing the exponentiation? Is it the number of clocks, or is it the
actually we have to, so first exponential comes from the region construction itself, right? The second is that we are actually considering the subset of the states of the region construction, so to solve this problem. So that is why we're getting doubly exponential in the state space, and then we are trying to solve the problem, then it goes back to p exponential space problem.
So then it's really the number of constants that you have used in the guards that is causing the exponential.
So for first exponential, yes, we have to consider the guards. The first region construction comes from the clock values itself. The second constant is that we have to make sure that, especially if you look at the definition of there exists resilience, the way it is defined, we have to, after case steps of the fault, we have to ensure for time case that both of the suffix occur at the same time. So to make sure that we are actually apply some kind of, again, we have to take the subset of the regions on which to follow the same time stamp at some point of time, follow the same global regions. Okay. So that is why we have to again apply another subset operation on the states of the region automata. So that is why we are getting double exponential in the state space, and then in space complexity we are getting it X space.
Okay. So if you take the number of constants that you have used in the guards as a constant instead of input parameter, then will your analysis essentially give a p-space per bound?
So you are saying that the guards, instead of taking it from the time automata, we are just allowing something, I don't know, it will improve on that. Because anyway, if we have, no, I don't think that would improve.
Okay.
But I have to think about it. I'm not sure.
Yeah.
Yes.
Okay. Sure. Any other questions? Okay, if not, let's thanks Parsha again for the talk, and
Thank
we
you.
will move on to the fourth talk by Nicolas Biron. We'll talk about branching automata and poset automata. Over to you, Nicolas.
Can you hear me?
Yeah.
Yes? Okay. So thank you for the introduction. In this talk, I present some new results on branching automata, which are a generalization to POM sets of automata on words. The first result is that with a very slight variation on branching automata, they are exactly as expressive as context-free grammars. The other results consist in characterization of series parallel rational languages, which are a particular subclass of rational languages of POM sets. Similar results that I will mention were also obtained by others on another model for automata on POM sets, which is called POM set automata, or P automata for short. In this talk, we focus on automata modeling for joint concurrency, which is widely used in practice. The principle is simple. A main process needs to execute several tasks in concurrency. It forks into n subprocesses and then waits for all of them to terminate. Then the main process joins the n results from the subprocesses and continues its run. This fork join principle is widely used in divide and conquer based algorithm, such as in the quicksort illustrated here, for example. Considering words as traces of sequential execution, POM sets are traces of concurrent executions. POM sets are built from a finite multiset of letters, equipped with partial orderings on the elements. The transitive and reflexive closure of the arrows in the picture gives the increasing ordering. For example, this B is less than this A, so the increasing ordering is from left to right. We need the two following operations on POM sets: the sequential product of two POM sets, which is also called concatenations. It is a generalization to POM sets of the usual concatenation of words, is obtained by taking the union of the POM sets, keeping the ordering relation inside each one, and saying that the elements from the first POM set are all less than the element of the second one. The parallel product of two POM sets is just their union, keeping the internal ordering. The series parallel class of POM sets is the smallest, which is built from the empty set, the singleton for letters, and closed under sequential and parallel composition. It is well known that series parallel POM set corresponds exactly to the N3 POM sets. We also need the notion of substitution of a letter in a POM set by some POM sets. Take a POM set P, a letter, which here is B, and a set of POM sets L. Then the substitution of B in P by L consists in replacing non-uniformly in P each B by a POM set of L. Since here there are two B's in P, and each B can be replaced by either the POM set in blue or the POM set in green, then the substitution is the language composer of those four POM sets. From the previous operations, we define the B-star rational languages, which is the smallest class contained in the singleton for all letters, and closed under a finite union, sequential and parallel product, sequential and parallel iterations, substitution, and an additional operation that allows to iterate substitution over a language. Here we iterate the substitution of the letter Xi over the language L. We now give a first definition of automata on POM set, where the empty POM set is not considered at all. A branching automaton is a usual clean automaton on words, with additional fork transitions that start parallelism. That goes from one state to several states, at least two. And there are also joint transitions that end parallelism that start from at least two states and goes to one state. Fork transition and joint transition are not labeled by letters. Fork transition are colored in blue and joint transition are colored in red. If you have n passes from state Si to Ti, labeled by Pi, then you and a fork transition from a state S to all the Si and a joint transition from all the Ti to state T, then you can build a path from S to T, which is labeled by all the Pi set in parallel. Note that epsilon is not, the empty POM set is not considered at all in passes, and in particular that the Pi here are all non-empty. Consider, for example, the following branching automaton. It has one fork transition and one joint transition here. And the following POM set. Then you have a path from state 1 to state 4. Reading the letter is as usual, and reading a parallel POM set starts with a fork transition and ends with a joint transition. Now we slightly modify branching automata in order to allow passes labeled by the empty POM set epsilon. For every state S, we have a path from S to S labeled by epsilon. We call B-star automata such automata. There is no epsilon transition, but in particular, the empty POM set is allowed in parallel parts of passes. This allows, for example, to define context-free languages of words like A to the N, C, B to the N. B-regular languages are those definable by a B-star automata. Extend the usual context-free grammar on words to POM set by allowing the parallel operation in rules. Our first result is that a language is B-star regular if and only if it is context-free, if and only if it is B-star rational. Now we turn to a particular subclass of B-star rational languages, which is called the series parallel rational languages. They are defined as B-star rational languages, except that substitution cannot be used anymore. Then a language is series parallel rational if and only if it is a language of some B-star automaton, such that there is no path that starts with a fork transition F, ends with the joint transition J, and contains a subpath that uses again the pair Fj, and which is concatenated either to the left side or on the right side or on both sides with a non-empty path. We now turn quickly to another definition for automata and POM set. We replace the fork and joint transition by a new kind of transition that are called parallel. They are used to start parallelism, but also define where to join. For example, this transition here starts from P, two parallel flows, one from P1 and the other one from P2. Each parallel flow runs until reaching a final state. Then parallelism can end and join to go to state Q. Here is a P automaton with language A to the N, C, B to the N that we previously defined using a B-star automaton, and a path which is labeled by A2, C, B2. Then a language is P-regular, that means definable by a P automaton if and only if it is context-free. As a consequence, P automata and B-star automata have precisely the same expressive power. There is also a characterization of P automata, which is related to series parallel rationality and is based on the pre-ordering of states related to the notion of accessibility between states, and uses some simple syntactic condition that every state which is source of a parallel transition must verify relatively to the pre-ordering. A similar but more complicated and less elegant result holds for B-star automata with two preorder instead of just one. The first preorder is linked to fork transitions and the other to joint transitions. So this is the end of the talk. Thank you for your attention.
Thanks, Nicola, for the talk. We can take questions. Okay, looks like there are no questions. So let's thank the speaker. Thanks, Nicola. And
Thank you.
so this is the end of the session. Any announcement by the organizing committee? No. So then the next session will be at 4:45 after the break. Thank you.
Such
Sorry, thank you. Liam, so from my side, your video is frozen. I don't know if you can hear me. The screen share just started.
It was also frozen for me.
Okay. So let's wait 2 more minutes. I'll try to send him an email. Ah, there he is. Hey. Can you try to say something? No, you muted.
Hello.
Yeah.
Sorry about that. I
Cool.
started uploading in the house and I got kicked off. I apologize for that.
Okay, no problem.
Shall I start? So
Yes. Yes.
Okay, perfect. Apologies again. Okay. Can everyone see? Is this working? Yeah. Okay, cool. So hi everybody. My name is Liam Jordan. I'm a PhD student in Maynooth in Ireland. And today I would like to present a talk that was done alongside my supervisor, Philippe Moser, titled Normal Sequences with Non-Maximal Automatic Complexity. So in the paper, what we were interested in was examining normal sequences. So by a sequence, I just mean an infinite concatenation of zeros and ones. And specifically what we did was we examined the ratio where if we took the automatic complexity of prefixes of the sequence and we divided it by the length of the prefix we were examining, we looked at the two ratios when we took the lim sup and when we took the lim inf. And these two values are always going to be between 0 and 1, 0 being least complex, 1 being most complex. So just so we're all on the same page, what do I mean by a normal sequence? Well, a sequence is normal in base K if for every string X of length N, X would occur as a substring in S with asymptotic frequency K to the minus N. So in our case, we're dealing with binary sequences. So for example, all strings of length 2 would occur a quarter of the time as we look at longer and longer prefixes. So just some simple examples of base 10 normal sequences. If you were to list out all the non-negative integers in order, that's normal. And similarly, if you were to list out all the primes in order, that's normal too. Okay, so what is automatic complexity? Well, it's a type of finite state complexity introduced by Shala and Wang in 2001. And essentially, it's a type of distinguishing complexity for DFAs. So specifically, the automatic complexity of a string X of length N, which we denote by A of X, it's the smallest number of states required by any DFA M, such that X is the only string of length N that M accepts. So in essence, what we're looking for is some DFA that does the following. If the input is X, we accept. If the input has the same length as X, but isn't X, we reject. And otherwise, we don't care what the DFA does on other inputs. So a very simple example would be all strings that are just composed of zeros. They all have automatic complexity of 2. And that's witnessed by this DFA here. Because, for example, if you look, the only string of length 3 that is accepted here would be the string of 3 zeros. So why were we interested in examining normal sequences? Well, in many finite state-based complexity approaches, normal sequences are the most complex. So a famous example would be if you were to define finite state complexity based on compression by information loss as finite state compressors, you would find that a sequence is normal if and only if it's incompressible by all finite state compressors. So in that case, normal sequences are the hardest sequences in that scenario. So with automatic complexity being a finite state notion, we were interested in the question, is this also true for automatic complexity? i.e., is the lim inf of the ratio we examine always equal to 1 for every normal sequence? And if not, how low can it go? So our first result in the paper was that we were actually able to build a sequence, a normal sequence, such that that lim inf of the ratio can actually get arbitrarily close to 0. And for that same sequence T, we showed that the lim sup is bounded above by a half. And to do this, we used a construction by Nanda Kumar and Vangapelli, which essentially gives us an easy way to construct normal sequences, which is just, and all you do is just take the Browne strings of increasing order and concatenate them with themselves several times. And this means you get lots of repetitions. Repetitions mean we can use loops in our DFAs, and loops will reduce the number of states we need. So our second result was based on, I guess, Champer-known sequences. And these are a special type of normal sequences where to construct them, you have to list out all strings of length 1 exactly once, and then you list out all strings of length 2 exactly once, and so on. So their construction is kind of restricted in a way. And so we wondered, with this restriction, must Champer-known sequences have maximal automatic complexity? And what we were able to show was that, in fact, this is not the case. We showed that there exists a sequence C such that when you take the lim sup of the ratio we're interested in, it's bounded above by 2/3. And to do this, we used a construction by Pearson Shields from the year 2000. And again, this method also uses de Bruijn strings in its construction. So for example, just so you can get a visualization of what's going on, this would be C4. So this is when we list out all strings of length 4 exactly once. So you just concatenate these 4 rows together to get your substring. As you can see, there's lots of repetitions and lots of patterns going on here, which is good for us. C5 looks like this, and C6 would look like this. Again, lots of patterns, lots of repetition, so which means loops. So just do a quick example, I guess. So let's say my prefix is X, and the largest, I guess, substring, or the largest zone that's a substring of X is Cn+1. So I've managed to list out all strings of length n+1, but not all strings of length n+2. So what would my DFA look like? Well, if n is a power of 2, my DFA would look like this. So I would come along reading the beginning of my sequence or my prefix bit by bit by bit up to zone Cn-1, and then I'd read n zeros. And then I would traverse this loop n times to read the substring Cn. And when I'm finished that, I would traverse here, have a state for each bit I read until I come to this loop. And then I would traverse this loop n+1 times. And then depending on how much of zone Cn+2 I read, I would traverse along here, reading state by state, until I come to an accepting state. And the fact is, because this loop has odd length, so the string I read when I traverse this loop has odd length, and the string I read when I traverse this loop has even length, there's only one way for us to traverse these loops such that we end up with a string whose length is equal to the length of the prefix we're examining being accepted. So what I mean is, it's impossible for us to traverse this loop some number of times and this loop some other number of times and end up with another string of length X being accepted by the DFA. So this is impossible. So the prefix is the only string that's accepted by this DFA that has the length we're interested in. So I guess some questions or future work I'm kind of interested in. For the upper bound for the Champer-known sequence, could it be tightened? So in all the proofs we use, we only use 2 loops. So is there a way for us to use 3 loops or 4 loops to maybe shrink this, make this bound tighter to shrink the upper bound? The lower bound, the lim-inf of the ratio, we don't really have much about that either. The best we know is that it is bounded above by 1/4. But ideally, I would have some kind of result where I could say the lim-inf of the ratio is always bigger than 0, or maybe it's always bigger than 1/8. Again, I don't know. Maybe there's some kind of argument from number theory that's pretty straightforward that I'm just not seeing. So if anyone has any ideas or gets a chance to look at the paper and get some ideas, I would love to hear from you. So thank you very much, everybody.
All right. Thank you very much, Liam. Are there any questions? So I have, big one.
Yeah.
Thank you. You consider the lim-inf or lim-sup.
Yeah.
Would it be also maybe make sense to consider something, not that maybe infinitely often you have low automatic complexity, but maybe with positive density you have low automatic complexity. That kind of.
Yeah, I know in the original paper, when they talk about strings, they have lots of results such as that in the original paper. So they have like with positive density, for example, that a string X, so with positive density, you can say that the automatic complexity of a string is less than 3/4 plus some other term. I'm not entirely sure. So there is work done on that specifically on strings. On sequences, yeah, that's something that's possible to look at. So yeah.
Okay. So my question would be, can you, I mean, it sounds like this is a very purely combinatorial question,
Yeah.
but
yeah.
Is there a way of doing any of this effectively? So given, let's say, an automatic sequence, can you say anything about the complexity of it algorithmically?
Ooh, in terms of like what its value is, or finding it, if you understand me.
Anything. So, for example, can you decide if the complexity is 0? That sounds like it should be possible, no?
No, you have to kind of, I guess, if there's a way to do it, I'm not familiar with it. It's kind of a case of trial and error, build your DFAs. So if that's what you're asking me.
I'm asking, for example, is there an algorithm that, given an automatic sequence, an automatic sequence is one where, given a binary representation, you have a DFA that tells you if there's a 0 or 1, that tells you if the complexity is 0.
No, there's not to my knowledge, and there's no algorithm to actually, if given a sequence, to calculate its complexity. Not to my knowledge,
but
anyway.
Would that be the holy grail of this line of research?
I guess so. Yeah. It's quite new in terms of examining sequences. It's not looked at often. I think there's really only one other person who kind of looks at it on a regular basis. Yeah.
Okay. So, any other questions? Doesn't seem like it. Okay, we're only 3 minutes over that time. So let's thank the speaker again.
Thank you.
And now the next speaker is Christopher Hugenroth.
Yes.
And he's talking about separability of regular languages by levels of the Wagner hierarchy. Go ahead, Christopher.
I hope everybody can hear me and see my slides. So yeah, I'm going to talk about separating regular languages over infinite words with respect to the Wagner hierarchy. And we're going to look at finite automata. So we have finitely many states, and we have infinite words. So in infinite word, we'll have an infinite run over this automaton, and some states will be visited infinitely often. And we call such a set of states that might be visited infinitely often a loop. So for example, in this automaton, the word that only consists of A will loop in P1 infinitely long, and the word AB, and so on will loop between P1 and P2 infinitely often. And I will denote these loops as ellipses in the automaton. And based on these loops, we can define languages over infinite words. For this, we use a deterministic Muller automaton, and a DMA accepts an infinite word if it ends in a loop that is contained in a set of accepting loops. So accepting loops, I will always color blue. So this DMA here, for example, would accept the word AB to the omega, but it would reject the word A to the omega. And this is a key difference to finite words, where we only have final states. And here we have loops, and these loops, they have a relation between each other. So for example, this red loop is a subloop of this larger blue loop, and the red loop P3 is reachable from the blue loop. And this gives a certain loop structure to this automaton. And this is what Wagner studied. And he defined what is now known as the Wagner hierarchy. In this hierarchy, we have infinitely many classes of languages, and a class is contained in a language is contained in a certain class if there is a deterministic Muller automaton with a certain loop structure for the language. So let's, for example, look at the class C11. In there, we have languages that can be accepted by automata where all loops are accepting. So the only language that is contained in C11 would be the language of all infinite words. And then in C12, we may have one alternation from accepting loop to rejecting loop. And in G classes, we have the dual condition. So there we have first rejecting loops, and then we might reach an accepting loop. So this would be like a reachability condition. And as we go up the hierarchy, we get more and more alternations. And then in the limit, we get new classes like D21, where we have rejecting loops that are subloops of larger accepting loops. This would correspond to a Behe condition. And then we can again iterate and go up this hierarchy. And it turns out that this hierarchy is really important because, for example, it refines the Mostowski hierarchy, and it also refines the Borel hierarchy for regular omega languages. So this is really a fundamental hierarchy, and it's interesting to decide, given a language, where this language is in this hierarchy, and this is known as the membership problem. So for this problem, we are given two numbers that describe a class of the Wagner hierarchy and deterministic Muller automaton. And we asked, is the language of the automaton contained in this class? And Wagner showed how we can decide this. He showed that the loop structure is an invariant of the language. So every deterministic Muller automaton for language L has the same loop structure with respect to the Wagner hierarchy. To decide the membership problem, it suffices to check the loop structure in the given automaton A. Okay, so we are given two numbers in the automaton A, and all we do is we look at the automaton, at its loop structure, analyze it, and decide in which class the language of this automata is. And then we know, because it's an invariant of the language, that every other automaton for the language will have the same loop structure, and we are done. And this has been known for quite some time. And I looked at a more general problem, which is known as the separation problem. And separation has been studied in many settings, for example, for the first order alternation hierarchy. And this is a slightly more general problem, because now we're given, again, two numbers that describe some class of the Wagner hierarchy, and now two deterministic Muller automata. And we asked, is there a language L in a class CMN of the Wagner hierarchy that separates the languages of the automaton? So the language of the first automaton should be contained in L, and this language of the second automaton should be disjoint from L. And yeah, this seems more difficult than the membership problem, because for the membership problem, we use that we have a representation of the language L, right? We had this automaton A, and we just checked the loop structure on it. That was easy, but now we asked, is there such a language? And we don't have a representation of it. And the main idea of my paper is that we can just use the product automaton of A1 and A2 and check the loop structure in there. For that, we, of course, have to define what exactly is the product automaton and what is a loop what is the loop structure in the product automaton. And this is what I do in the paper, but in this talk, I won't have time for it. But if you're interested, you can look at my pre-recorded video. There I explain this. But if you do this, you get a nice characterization of separability. Namely, the languages of A1 and A2 are separable by a language in CMN if and only if the product automaton is at most MN forcing and every MN superchain in the product automaton is red start. So all these terms like MN forcing, MN superchain, and red start, they refer to the loop structure of the product automaton, and they can be checked. And one result one gets from the proof of the theorem is actually that if we are given two Malloy automata A1, A2, then we can construct a separating Malloy automaton that is minimal with respect to the Wagner hierarchy in exponential time. This can be done by just using the product automaton and then fixing, accepting, and rejecting loops in there. But it cannot be done faster because this separating deterministic Malloy automaton might be exponentially larger than the input automata. This is because we might get exponentially many loops which are accepting, and therefore the acceptance condition might get exponentially large because we have explicit Malloy acceptance. But it turns out that if we ask whether we can decide separation, so we just want to know, is there a separator? Then we can do this in polynomial time because we have just to look at certain loops in the product automaton and we don't have to construct it explicitly. And for future work, it might be interesting to look at other acceptance conditions. If maybe there you can construct a separator in polynomial time and you don't have this exponential blowout. Thank you.
Thank you, Christopher. So, are there any questions from the audience? Okay, not at the moment. So, I have two questions. So, the first is you already touched on that a little bit. You say the separating automaton might be exponentially large, but is there maybe a simple way of describing the of compressing it? So let's say if the acceptance condition just says all the subsets of this set, then obviously you introduce some syntax that says this.
Yeah. I looked for it for some time, and something like Rabin or street acceptance looks complicated because you can't simply construct a product automaton. It turns out to be rather difficult. But we could look at something like Silonka trees, which are smaller representations of Malloy acceptance, or Silonka ducks, which are even smaller. I actually defined a new acceptance condition based on this paper, extension acceptance, which is again similar to Silonka ducks. And in there you just store some blue and some red loops, and some loops have no color, and then it might be possible to get a smaller separating automaton. Yes.
Okay.
This is just a silly question. Maybe I missed it. So the number of states is small. It's what's exponential is the acceptance condition. Is that correct?
Yeah, exactly. It's also if you have intersection of deterministic Malloy automata, then it's the same. You have small states, but a large acceptance condition. Yeah.
Okay. Another very quick question. There's a more general version of separability where you have several input automata, and you don't need them to be all disjoint, but you only need to be the intersection of all of them disjoint. And then you're asking, can you wrap each of them in an automaton in the smaller class so that these over approximations are empty? Does the same technique apply? Don't say it might.
Is it now that you can, it seems like you could reduce it to just testing 2 automata if they are disjoint?
No, I don't think in general. They don't have to be all, it's not the same as being pairwise separable.
Okay.
But okay, this is something for future work.
Yeah.
Okay.
Maybe I don't know.
Okay. Thank you. So let's thank the speaker again. And now we come to, I think Petra is giving the talk on intersection non-emptiness for star-free regular languages. Go ahead, Petra.
Yeah, thanks for the introduction. So this talk is on the complexity of the intersection non-emptiness problem for star-free language classes. And it is based on joint work together with Emmanuel Arrighi, Henning Fernau, Stefan Hoffmann, Markus Holzer, Ismail Jecker, and Mateus de Oliveira. So first of all, what is the intersection non-emptiness problem? So formally, we are given a set of finite automata. So we are back in the finite setting here, no infinite words, just finite words. And we want to know whether there exists a word that is accepted by all of the automata, meaning that the intersection of the languages of the automata is non-empty. And the motivation of this problem is you can think of that you want to monitor a system and you can just read a protocol and you want to check that several properties are satisfied by the protocol at some point simultaneously. Then you can model this as an intersectional emptiness problem where each automata is monitoring one property and you want to find a position in the protocol such that all of the properties are satisfied, meaning that all of the automata accept the string describing the protocol up to this point. And then you can send a signal and do something with this information. And the complexity of this problem is in general that it's p-space complete. And only a few special cases of the problem have been considered so far. So for instance, if we restrict ourselves to unary alphabets, then the problem becomes NP-complete. And what we did here in this project is we took a closer look at the intersectional emptiness problem and considered it for 2 infinite hierarchies within the class of star-free languages. So first of all, what are star-free languages? There are several ways to define this language class. For instance, one is over star-free expressions. Those are regular expressions using concatenation, union, and the complement instead of the clean star. So the clean star is not allowed here. Another way to define the language class is via the syntactic monoid, namely the star-free languages are those languages where the syntactic monoid is aperiodic. And even if this class of languages looks quite restrictive, it is still rich because it contains the 2 infinite hierarchies, namely Straubing-Thurniaux hierarchy and the Cohen-Brosowski-Dotdev hierarchy. In order to define these 2 hierarchies, we first need to define 2 closure operations. The first is the Boolean closure. And the Boolean closure of a class of languages is the set of languages obtained by applying finite union, intersection, and complement of languages in the class. And for the other closure operation, we need the marked product. And we say that a language is a marked product of a sequence of language if it is the concatenation of the sequence of languages with special letters in between. So a word in the marked product consists of a word from the first language, then a special letter, then a word from the second language, and so on. And these special letters here can also appear in these languages LI. Then with the marked product, we can define the polynomial closure. A polynomial closure of a class of languages is the set of languages that we obtain with finite unions of marked products of languages from this class. And with these two closure operations, we can now define concatenation hierarchy. Concatenation hierarchy of a class of languages is in the lowest level, level 0, just the class itself. And then we go to the next half level by the polynomial closure of the last full level, and to the next full level with the Boolean closure of the last half level. And now we can define the Straubing-Taryon and dot-depth hierarchy, because there the Straubing-Taryon hierarchy is the concatenation hierarchy of the class containing only the empty set and sigma star. And the dot-depth hierarchy is obtained by taking the set of all finite or co-finite languages as the starting class. The relation of these two hierarchies is that the Straubing-Taryon, that each level of the Straubing-Taryon hierarchy is contained in the same level of the dot-depth hierarchy, and the dot-depth hierarchy is contained in the next +1 level of the Straubing-Taryon hierarchy for each level. And when considering the intersectional emptiness problem, we need to make use of the promise that when we restrict ourselves to some level of each hierarchy within the problem, then we have the promise that the input automata are accepting languages of this level. Because determining the exact level of the languages accepted by a given automaton is in general a hard problem. So it's in general p-space hard. And even for level 3 of Straubing-Taryon, it's open whether it's decidable at all. So we need to have this promise, because checking this property would be too expensive and we wouldn't see any details in the complexity of the intersectional emptiness problem. So now I want to give you just a picture of our results, and we start with the NFA case. So in general, we know that the general problem is p-space complete, both for NFAs and DFAs, meaning that for every level we have membership in p-space, and we get the p-space hardness already for dot-depth level 1 and Straubing-Taryon level 2. Then we have NP hardness starting from dot-depth level 0 and Straubing-Taryon 1, meaning that as soon as we have the set of all finite languages, we have NP hardness here. And in the case of NFAs, we only have NP membership also for the level 0 of the dot-depth hierarchy, but we don't know the case for these three classes here in between. So we don't know the precise complexity of dot-depth 1/2, Straubing-Taryon 1 and 3/2 in the case of NFAs. If we go further down, so for Straubing-Taryon 1/2, we have both NL hardness and membership in NL, and even lower, for the lowest level 0, we have membership in AC0. So this is the picture for NFAs as input. If we look at the DFAs as input, then this gap here is solved. So we also have membership in NP for these three classes here. And down below, the picture for Straubing-Taryon 1/2 changes from NL completeness to deterministic log space completeness. So this is all I can show you in this short presentation. If you want to learn more, then we'd be happy if you watch the full presentation or have a look at our paper. Thank you.
Thank you very much, Peter. Very nice. Any questions from the audience? So I would have a question. In the case of NFAs, you said that the level L1, L3 halves, and B1 half are NP hard, but you don't know if they're in NP. So do you know if so are there examples where the smallest word in the intersection is more than polynomially long? So actually, no?
So for the smallest word in the intersection, I'm not sure at the moment, but the thing is that so we have the DFA case we are getting by a characterization of this level here, Schreiber-Tollian 3½ by partially ordered NFAs, and we have like a relation between the size of a DFA and the size of an equivalent partially ordered NFA. And this relation does no longer work if we have as input general NFAs, because a general NFA can be exponentially smaller than a partially ordered NFA. So, and we show that we have examples for that.
I see. So in other words, in the DFK, you use the fact that if there is a word in the intersection, there's a small word.
Yes.
And because sometimes for these problems, it makes sense to look at compression schemes and instead of guessing a long word, guess a compressed word. Maybe that's something we could look at. All right. Any other questions? Okay, so let's thank the speaker again. And now it's time for the last talk. We have both authors here, so I don't know. No, I think Carolina wanted to give the talk.
Yes, I'm in charge of that.
The next talk is by Carolina Lehtinen on history determinism and good forgiveness in quantitative automata. Go ahead, Carolina.
Thank you. So this is joint work with Udi Berker. And yes, we are working on history determinism and good forgiveness in quantitative automata. And here, history determinism and good forgiveness are two intermediate forms between determinism and non-determinism, the idea being that when we look at such intermediate forms, sometimes we can get some very nice trade-offs between some of the good algorithmic properties of determinism and some of the expressivity of non-determinism. With Udi, we have been working on history determinism and good forgiveness in the omega regular setting for a while, and there history determinism and good forgiveness are used interchangeably as they coincide. So one of the surprising things that happened when we moved to look at what happens when we add weights onto our automata is that, well, these two notions are now different. So what we do in this paper is we explore why this happens, what's going on here. We define some related notions that I'll go over and look at the landscape of what is going on there and how these different notions relate to quantitative synthesis problems, since solving reactive synthesis is one of the main motivations for looking at history determinism in the first place. So just a quick recap of what we mean by quantitative automata. Well, in this case, they're just automata where we have weights on transitions. So a run will produce a sequence of weights which we accumulate into a single value using some kind of value function. So this could be, for example, sum, it could be the supremum, it could be the lim sup, the limit average, etc., etc. We consider these things both on finite words and infinite words. And then the value of a word is given by the supremum of the values of the runs over the words. So like a max plus automaton would be a particular case, but we consider other value functions too. In the paper, we actually deal with alternating automata, where we also have the dual of non-determinism, which we interpret as the dual of a supremum, so the infimum. Okay, now once we have these automata, we can talk about history determinism, which in a nutshell means that our automaton is allowed to have non-determinism in it. So it's not a deterministic automaton. However, we have to be able to make our non-deterministic choices without guessing the future of the world, so without knowledge of the future of the world. So in other words, we need to be able to build an optimal run on all words, letter by letter, without knowing the future. So that's kind of the intuition behind history determinism, which we formalize with this notion of a resolver that takes the run so far, the next letter, and tells us where to go. And we ask for that function to induce an optimal run. In the paper, we also define a notion of threshold history determinism, where rather than having to build an optimal run, we ask that our resolver just has to build a run that achieves some threshold for all words that have value above that threshold. So there we get closer to the Boolean definition where our resolver has to build an accepting run when such a run exists. And here it's important to note that we can have a different resolver for different thresholds. Why we care about history determinism? Well, history deterministic automata can be more expressive than deterministic ones. This is the case, for example, for history deterministic pushdown automata. They can be more succinct. This is already the case for Kobuchi automata in the omega regular setting. However, despite this additional power, they are well behaved because quite often they behave just like deterministic automata. And this in particular means that they are good for games, which is our second important definition. So while history determinism refers to this existence of a resolver that finds a good run, the definition of good for gameness is much more functional about what can the automaton do. And the intuition is that an automaton is good for games if we can compose it with games and the composition is well behaved. And here well behaved means it's as if the automaton was deterministic. In other words, it should preserve the value of the game. So in the quantitative setting, of course, we are talking about quantitative games where we have two players. They move produce letters. So a play will produce a word. And the value of the play will be the value of the word as given by our quantitative automaton. And we have one player who's trying to build a word that has a very good value, and another player who tries to minimize that value. Now, when we take the product of such a game with an automaton, we still have our original game that produces letters, but in addition, we have the automaton that consumes the letters as they are produced. And since we have non-determinism, we have Eve, who is trying to maximize, who gets to pick which transition of the automaton we choose. And she has to make this choice as soon as we produce a letter. So she will pick a transition over that letter in our automaton to advance in parallel in the automaton. So now the composition game both produces a play in the original game and a run of the automaton, and the value is given by the automaton. And here we have, again, Eve maximizing and minimizing, and we say that our automaton is good for games if this composition preserves the value of all games. We also have the threshold version of this definition, which cares about whether the Eve can achieve a fixed threshold. And essentially, this definition allows us to reduce games with arbitrary payoff functions into games with standard payoff functions, such as discounted sum games, for example. So the kind of heart of our paper is comparing these definitions. And the highlights there are that, well, good for gameness and history determinism do not coincide. We analyze why they don't coincide and find that it is this, at least part of the reason they don't coincide is that history determinism and threshold history determinism do not coincide. Namely, having this resolver that can depend on what threshold is trying to achieve, gives it more power, and that threshold history determinism is then closer to the notion of good for gameness. We also compare these notions with determinizability by proving, which is the notion of having an equivalent deterministic automaton embedded in our original automaton. And in our paper, we give conditions of when this coincides with history determinism. In particular, it is the case for various fairly common value functions, in particular for sum, average, inf, sub, and discounted sum. Then finally, we look at how these different notions can be used for quantitative synthesis, where, well, for good for gameness, the story is very much the same as in the omega regular settings, namely, if you have an automaton, if you want to synthesize a specification given by a good for games automaton, you can do the product and solve the product game. So it's kind of what you would expect. But we also observe that a slightly different version of the quantitative synthesis problem, which instead of asking for Eve to maximize the worst case outcome, which is what the generalization of the church synthesis problem to the quantitative setting does, if instead we ask Eve to behave optimally on all behaviors of the environment, then we get that's what's called best value synthesis problem. And that is polynomially equivalent to deciding whether an automaton is history deterministic. So if you have the best value function, the best value synthesis problem for a deterministic automaton is equivalent to deciding whether an automaton is history deterministic, which kind of motivates studying this history determinism problem further. I think that's my time, so I'll leave it at that, and both me and Udi are here for questions and discussions.
Yeah, thank you, Kalina, for a very nice talk. Are there any questions from the audience?
Can I ask so when you threshold history determinism and non-threshold do not decide, which kinds of acceptance conditions does that require?
It does not require very much. We have this very simple example where, well, we have a non-deterministic choice to either go to a state that gives me value 1 for all letters, or a state that gives me value 2 or 0, depending on the letter. Okay, so this can be a sub, sum, whatever automaton. You don't need very much at all. You just need 3 values. And this is not history deterministic because you have to guess the second letter to get an optimal run. However, it is good for games because if in your game Eve has a strategy that guarantees 2, Eve guarantees that the second letter can be forced to be a 2. So then Eve can use that information to go into the lower state in the composition and achieve value 2 in the composition game. While if the game has value 1, then Eve only needs to achieve 1 in the composition, which means that she can go into the upper state. Thank you for the question. I appreciate getting to use my extra slide.
All right. Any other question? Okay. Then we're also almost at the end of our time. Use up the additional slot. So thanks again to all the speakers of the session. This was very nice. And so, yeah, see you soon, everyone.
Thank you.